Okay, the diffusion and effusion. No. So the difference between diffusion and effusion, they're very similar. It's all because gases move at constant random motions. But diffusion is the spontaneous mixing from random motion, and that would be like if you open a strong bottle of vinegar in the back, eventually you'd smell it. Or when you spray Febreze in the front, usually you can smell it in the whole room because it will diffuse to the rest of the room and fill that container. The rate depends on speed, so the faster the molecules are moving, the faster it will diffuse. And temperature is what can change the speed. So at higher temperatures, the speed is moving faster, so usually it'll diffuse a little faster. Diameter of the molecules, larger diameters diffuse a little slower, just because they're larger. If they have strong attractive forces, they're going to diffuse slower. And then effusion are particles under pressure passing through tiny openings. Can you think of an example of that? Gas particles under pressure passing through tiny openings. Yeah. But you're exerting more pressure on it. No? That's a good example where you have balloon. You know, even if you have tide and everything, eventually it just shrinks, right? No. The air compressor? Tire. Yeah, I think that's not a small enough opening.
Like a tire,
if you run over a nail, even though the nail's there, you have leaks around the outside. If you pull the tire out, then it's a large opening, and I wouldn't consider that effusion. But, yep. Whoa. I think that was an example of both of them where this is diffusion. I think this is like hydrochloric acid and ammonia, and they would form a solid when you mix them, but the gases are diffusing and they're actually forming a solid in the air. So you can see the gases, that's one way you can actually see it. And then here's effusion where there's a tiny, this is a vacuum, so there'll be no gas particles, tiny opening, gases will go through. So Graham's law of diffusion and effusion really is comparing the rates depending on velocities and the masses. So the rate is basically the velocity, and then the molar mass of the compound. So the velocities are inversely proportional to the molar masses, and you have to take the square root. So notice the rate 1 and molar mass of 1, they're opposite each other here. 2's are opposite. We really won't deal with the density part. We're going to mostly deal with the molar mass part. Can I switch it? So if a flammable gas is made up of only carbon and hydrogen, is found to fuse through a porous barrier in 1.5 minutes, under the same conditions of temperature and pressure, it takes an equal volume of bromine vapor, 4.73 minutes to fuse through the same barrier. Let's calculate the molar mass of the unknown gas, and then we'll try to figure out what that could be. So we have rate 1 over rate 2. Which one do you want? It doesn't matter. Our rates are the 1.5 and 4.73. How do you want to set it up? Okay. And they're both minutes, so minutes actually cancel out. It's equal to the square root Okay, so since 1.5 is this unknown gas, the molar mass of the unknown gas has to go on top or bottom? Bottom. So we're going to put an M there. So we're going to solve for the molar mass of that compound, and the molar mass of bromine will go on top. What's the formula for bromine gas? Br2, right? So bromine is 79.9. So multiply that by 2. So what are we going to do first? So what would you do first? Okay. You could actually divide this out and then square it, though. But yeah. Divide it out, square it. After you square it, it's 0.1. So that's equal to 159.8 over m. So how do you solve for m? Yep, 159 divided by 0.1. After you divide these two and square it to get rid of the square root. So what do you get for the molar mass? Wow, that seems really high.
16.
$16 sounds better, but I think it's the 1,000.
Yeah. 1,588.
88? Oh, I didn't round the 0.1. Yeah, I got 1,588. Mm-hmm.
I thought it took longer if it had a bigger molar mass.
Yeah, something doesn't seem right on that. 1,000 seems so big. Did we do that right? Point 5, we have to have that opposite. Huh? Because m is on bottom. So you have to multiply by m on both sides. And that means you have to divide by the 0.1. What if you flip everything? You should get everything the same. Try just flipping it. It shouldn't really matter, but no, I get the same answer both ways. That's strange. I didn't think it was that big. 1,588. Let's not figure out what that gas would be. Did we do the molar? That just seems so big.
I think we did it.
And this is a humongous molar mass. And that should go slower. Something's not right there.
Are you supposed to have the molar mass of bromine on the right or on the bottom?
No, because we put the rate of bromine on bottom here, so it needs to go on top. I don't know. Let's go to the next one, see if it looks better. What? But if we put the rate of bromine on the bottom here, the molar mass of bromine needs to go on top. Mm-hmm. Well, let's look at the next one, see what we get. Yeah, I did too, so. Oh, let's go to the next one, see if that one makes more sense. Sample of hydrogen infuses through a porous container 9 times faster than an unknown gas. So if our rate of hydrogen is like 9, the other one would be 1, 9 to 1. When it's unknown gas, so if the hydrogen is 9 times faster, that means the mass of hydrogen has to go down here. And we'll put an X there. So let's try this one and see if it gives us better. So we should have something heavier since it's slower. I got 163. 0.62. Did you swear? Did you take 9 squared and then multiply by 2.02? This time you're going to multiply. Yes, and that makes sense because we need something heavier. It should be, yes. I don't know what was up with that. I'm going to have to look up that one, see if it was a problem in your book or something. That first one. It would be grams per mole, yep. Because this one is grams per mole. What's next? Next one. If a neon gas travels 400 meters per second at a given temperature, estimate the rate of diffusion of butane at the same temperature. So do you want the rate of neon gas on top or bottom? Okay, so we'd have 400, and we're looking for the rate of the other gas. So we're looking for X here equals the square root of molar mass of neon needs to be top or bottom? Bottom. 20.18. What was it? 58? So whatever you get on the right, you're going to divide by, or take 400 divided by that, right? I got 235.74. No. Because since this side doesn't have any x, you could just solve this whole side. Take the square root of that. Does that make sense? It's lighter, so, or it's heavier, right? Butane's heavier, so it's moving slower. Makes sense. 235.74. Okay, on this one where it says determine the molar mass ratio of two gases whose rate of diffusion is a ratio of 16 to 1, we have 16 to 1, and it's looking for the whole ratio, so it's just looking for that whole ratio. You can put it as an x there, that whole x. Basically, it's going to be 16 squared, right? So our ratio would be 256 to 1 then. That's what that means. Okay, nitrogen infuses through a pinhole 1.7 times as fast as another gaseous element, so we can have 1.7 over 1. Estimate the other element's molar mass. So nitrogen's mass needs to be on top or bottom? Bottom, and it's nitrogen is N2, so 28, yep. We're going to look for X here. Squared. And then it also says determine its probable identity. So what do you think it could be? What gas has about that molar mass? I think that's going to be our closest. Bromine. Actually, wait. Bromine gas is Br2. Krypton or chlorine, it would be Cl2, so that'd be 70.9. But krypton is 83.8, so krypton is closer than chlorine, actually. So let's go with... Yeah, but that's not a gas. So I'm going to say krypton would be our closest one. So it could possibly be krypton.
What's calcium?
Solid.
I thought everything to the right of the stair step line was.
No. Sulfur's not. Carbon's not. It's a non-metal, but it doesn't mean it's a gas. Okay, so far we've talked about ideal gases. So they behave ideally and they followed those 5 assumptions we had of the kinetic molecular theory. But real gases occupy space and exert attractive forces. Now, noble gases will behave ideally, but a lot of gases are going to have some sort of polarity and attractive forces between them. So if they're more polar, there's going to be more attraction and more deviation from ideal behavior. So under what conditions will gases most likely exhibit non-ideal behavior? It's going to be when they're going to be closer together. So what would make them be closer together? Higher pressure. If you're pushing on them more, they're going to be closer together. So higher pressure. Or low temperatures. If you get low temperatures, they start moving slower and they're going to be closer together. So high pressures or low temperatures will give you more deviation from ideal behavior. And so here they're looking at ideal gases when it changed, but actually when you look at these gases, their pressures and everything are changing. So real gases will behave like ideal gases when they're far apart, and so they'll behave like real gases at low pressures and high temperatures, because low pressures they're able to be spread apart from each other, and high temperatures they're going to be farther apart from each other also. So what we have for real gases is a modified ideal gas equation, and it's a really long one, but it's actually fairly simple to plug everything in. But it's called van der Waals equation. And gas pressure is decreased because of the intermolecular forces exerted by the molecules, so we have to take into account those. And the A and B are constants that you can find on table 5.3 in your book. Everything else will be the same. P is pressure, A is that constant you'd look up, N is the number of moles, and you square that over V squared. V is the volume. And then B volume, N is the number of moles, B is the constant, and then N is the number of moles, R is our 0.0821, and then T.
How do you know when to use 0.0821 and when to use like 8.314?
The only time you use that 8.314 is the root mean squared speed equation. Otherwise, you use the 0.0821. Okay, so let's try this equation. You're going to have to turn to page wherever 5.3 is, because I think we're going to need those values. So first we're going to look at ideal gas, and then look at the van der Waals equation and see the difference that we have. So using the ideal gas law, we have P. What's our pressure? That's what we're looking for, I guess. Volume is 5.2, and it's in liters, so we can leave it as that. Moles, 3.5. R is 0.0821. And our temperature in Kelvin, .310? 320. 320. So using the ideal gas law equation, what's our pressure?
P
17.7? Yep. Ideal gas law is the Pervner equation, yep. What was it, 17.12? Oh. ATM. Okay, so now let's use van der Waals equation. And what is that? P, which was what we're looking for. AN squared. It's NH3. So what is A?
A is 4.17.
4.17, and you just look that up on that table, page 161, times 3.5 squared over V squared. Oh, V. Okay, and now we have V plus NB, isn't it? Is that right? V minus, okay. N is 3.5. And B, that constant, what's the constant for B? 0.0371. Okay. Oh, yep. Sorry. We do. 5.2. Okay, and then N, and then it equals nRT, right? So we have 3.5 times 0.0821 times 320. Okay. So I'll solve it too and see if we agree. You will be given the equation, you'll be given the constants that you need. Okay. Check your answers. What do you mean? Probably not. Okay, I got 16.25. Can anyone else do it and agree? 16.25? Yeah? If anything, you could just go through, like find this whole part, write that number up here, find this whole part, write it up here, and this whole part, and then you take this, the right side, divide it by this part right here, and then subtract this part. Yep. Should get 16.25, which makes sense because the pressure is supposed to go down for real gases.
N is the number of moles, right? Not molar mass.
Right. N is number of moles.
And then you subtract.
This one. Yeah. Is that what you got? Good deal. Is that it? Another problem? You want to do another Van der Waals problem? Just a bunch of numbers? I'll write up the equation here, and then I'll calculate it if you want to check yourself, see if you can get it. Because what is, I guess I don't know what chlorine. I don't know A and B for chlorine. What's A for chlorine? 6.49? I have the ideal gas?
Yeah.
I haven't. I'll calculate it here just a second.
2.45
.0562. N. It's 38. 311?
Yep.
Okay, so PVN.
So you should get the same thing on both equations, right?
No,
No?
the Van der Waals should be lower. Okay, so for A, I got 45.54. And then Wow. Get 29.97. That seems really low. I'm going to recalculate that one, though. Is that all that the notes were? Okay. So you guys can work on your chapter review.
What chapter is this? 5.
You have about 10 minutes.
Why would partial pressure? Just 3 reps at 1 roll. That makes sense.
Nice. Is that hard? That's the actual feature. Is that hard?
It's different.
I know, but I mean, isn't it hard? It's not easy to do shoulder
It's just an cool bottle.
Yeah, that's what I got. Okay.